Okay, so this is where we were last day, but we had gone a bit further beyond this. Remember, our job was to variationally figure out the BCS wave function. And there, what we did was try to optimize or rather minimize the expectation value in the BCS wave function of this quantity H prime. H prime is a Hamiltonian, but from that you have taken away mu times n. This is just the Lagrange multiplier way of imposing the constraint that expectation value of n is going to be constant. That is the number of particles. And we worked this out and we found that this was what the expectation value came out to be. Well, we have made a small change that since we are only going to deal with real values for u's and v's from now on, I just decided to drop the conjugation sign. So these are just all real numbers, vk square, uk, vk, uk prime, vk prime. That was the result that we had found out the other day. And we also use the fact that uk square plus vk square equals 1 to write down uk is sine theta k and vk is cos theta k. And basically, this expectation value of h prime then in the BCS state became sum over k xi k cos square one-fourth bkk prime and trying to optimize this with respect to the theta case gave rise to the following equation. That was where we had essentially stopped. Or we just did a few more steps after that, but this was basically our primary thing. bkk prime sine 2 theta k prime. This is sum over k prime alone. And what we did to simplify the calculation a bit after this was define a few parameters, like we defined this quantity in the numerator here, this numerator, as delta, which depends only on k, of course. It has been summed up over k prime. So the result now only depends on k. And what I did was define this quantity with an extra minus half as delta k. Delta k, we will see that first of all, this quantity has a simple interpretation in terms of the energy gap in the spectrum, but that will come later. But at least we will see that in the model BCS Hamiltonian, where we assume a form for vk prime, which is similar to the form that we took for the Cooper problem, this delta k will turn out to be a constant, actually constant over a region and then 0. And then you will also see that, of course, that means that will happen only because we have taken a very special Hamiltonian there. That's a result that we are going to derive soon. But we do expect the delta k to be a rather slowly varying function of k otherwise. So for many practical purposes, even when we are not working within the BCS model Hamiltonian, we might take delta k to be a constant. Okay, so this is basically our starting point, and we also defined the energy Ek. I'm essentially following Tinkam's notation here. Delta k square plus xi k square, square root of that. And with that, what we end up with is the following. All these equations that we have written down, the first one becomes tan of 2 theta k that's trivial. I've just divided this by. And then a bit of trigonometry, a very trivial bit, essentially tells you the sine 2 theta k, which you can find out of tan. You just square and add 1 to it, you get the sec square, and then divide tan by sec, you get the sine. And this is, of course, twice uk vk. Remember, sine 2 theta k is 2 sine theta k cos theta k. That's twice uk vk. And that works out with delta k by ek and vk square minus uk square, which is cosine 2 theta k. Of course, that's a reciprocal of sec 2 theta k, and that works out with xi k minus xi k. Okay, this is where the sign. Remember, we said that in the last day that if xi k becomes very large, then you expect vk's to go to 0, and therefore this should become negative. And that's where the minus sign, that's what the minus sign does for us. So these are our basic starting equations. And we also wrote down one more equation from here, which essentially will tell us what delta k is. That's pretty straightforward. All you have to do is start from this equation, start from the definition of delta k itself. And in definition of delta k, you have this sine 2 theta k prime on this side, but we already have sine 2 theta k in terms of deltas. So if you put that in, what you're going to get is delta k, which by definition of delta k was simply minus half sum over k prime vkk prime times sine 2 theta k prime. So that will be simply delta k prime by ek prime. Okay. Or you can write this down more explicitly in terms of known quantities in this form. Sum over k prime vkk prime delta k prime by square root of delta k prime square plus xi k prime square. Okay, so this is our basic equation for delta k. Note that in this equation, presumably, vkk prime, the kk prime matrix element of our interaction term, is something which we know. Of course, that depends on which particular model we are using, but in general, we know what vkk prime are. We also know xi k primes because these are the single particle energy levels shifted from the Fermi level. So that's also known. So on this side, this quantity and this unknown, delta k primes are unknown. Of course, the delta k prime sitting on this side is basically the value at k equal to k prime for this same quantity on this side. Okay, so basically you have a bunch of rather complicated nonlinear equations relating the delta k's to themselves. So you have many delta k's, one for each delta, one for each k, and all of them are connected to each other through a bunch of equations like this, right? And this, of course, is what you need to solve in order to be able to, basically determine, when you solve this, what comes out is that it gives you the value of delta, and then you take the value of delta, plug that in here and here, right? Because once you know delta, then E is also known, the square root of delta square plus I square. So both of these quantities are known. You now can figure out Vk and Uk, which means you can figure out the wave function. Is this point clear? So that should be your strategy. You should solve this equation to find delta. Once you found delta, plug it here. It will give you Uk Vk. Plug it here. It will give you Vk square minus Uk square. In fact, because you don't even need to plug it in both. Even this alone will do, because you know that Vk square plus Uk square is 1. So this will immediately give you Vk square and Uk square. In fact, the only reason why you need this altogether on top of that is to determine the sign of Vk and Uk. This will only give you Vk square and Uk square, whether it's positive or negative, or whether they have the same sign or opposite sign. That's more important. Remember, in your wave function, you have Uk plus Vk dagger acting on the ground state. The actual signs, whether they are both plus or both minus, doesn't matter. What matters is whether they are the same sign or opposite sign. If both of them are minus, it's the same thing as both of them being plus, because that's just an overall minus sign. Or U being plus, V being minus, and U being negative, V being positive means exactly the same thing, because that also differs. These two differ from each other by just a change of sign. But what is important is the relative sign of U and V. Are they the same or are they opposite? That makes physical difference. Okay. So strategy is solve this equation, plug it back here, find out Vk, Uk, you're done. Essentially, you have found out the gap value. You have also found out the occupancy of various Cooper pairs, how many Cooper pairs are produced, and so on. You essentially know the entire wave function. The only problem with that, of course, is that this equation would be a very, very difficult equation to solve because you have delta k here, you also have delta k on the other side, and this quantity is another complicated nonlinear function of the same delta k's. So you have a sum of lots of complicated terms involving deltas here. So it's really not a simple equation to solve in general. However, sticking to the spirit of the Cooper problem, what BCS did, they took a very simple, assumed a very simple model for VKK prime. And the idea was simply this. VKK prime is a constant. It's attractive, so let's put that as minus V0. Wettingham calls this minus Vs, if I remember correctly. I just want to emphasize that this is a special value of taken, so let's call this minus V0. And when is this non-zero? When both K and K prime are close enough to the Fermi level. In other words, the energy for corresponding to K and energy corresponding to K prime are both close enough to mu. So remember, psi K is of course the energy minus mu, right? So when you say that energy is close to mu, you essentially say that psi K is small in size. So magnitude of psi K is less than some cutoff energy, which we are calling h cross omega c. Remember, this is something which we identified even the Cooper problem as something which is related to the Debye frequency. And psi k prime. This is important. Both of these, mod psi k and mod psi k prime, has to be less than some cutoff energy value, which is tiny compared to this h cross omega c is very tiny compared to the mu. Okay, right? So
Yes, sir.
and then 0 otherwise. This essentially is what Cooper said. The Cooper problem, we wrote this slightly differently. We wrote this as epsilon k minus epsilon f, or minus h cross square k square by twice m, as less than h cross omega c. But this essentially means the same thing. Okay. So this is our VKK prime. Now for this particular VKK prime, let's look at the equation for delta. Delta k, let me remind you once again, is this equation minus half sum over delta k prime by square root of delta k prime square as I k prime square. Now note, first of all, this tells you one thing. If mod psi k is greater than h cross omega c, so if your particle has an energy, the single particle set that you're talking about here, corresponding to the level k, has an energy which is different from the Fermi energy by more than h cross omega c, then what can you say about this quantity? Then VKK prime, remember, VKK prime is 0 whenever either this is more than h cross omega c or this is more than h cross omega c. Any one of them being more than h cross omega c will make VKK prime 0, right? So if mod psi k is greater than h cross omega c, then what happens to this side?
So it becomes 0.
It becomes 0,
0, sir.
right? So because doesn't matter what this is, this factor vanishes. So delta k is 0. So my gap function, which should depend on k, here of course it depends on k. If k is such that mod psi k is bigger than h cross omega c, this vanishes. But what happens if k is, say, mod psi k is less than h plus omega c? Then delta k obeys this equation, right? Equal to minus half, okay, v0 by 2. I've taken the minus v0 out. Remember, that's minus v0 then. Sum over k prime. Right? Important
Yes, sir.
question. Is this a constant or a variable? Does it depend on k or not? Does this quantity depend on k?
No, sir, it does not depend.
Okay, but that's a bit strange, right? You started with an equation like this, where delta did depend on k, right? Note that why did delta depend on k? If you look at the right hand side, it depends on k only because of the vk k prime, right? Nothing else depends on k. But the matrix element between the states with momenta k and k prime of v, that of course depended on k in general. But because we have taken this very simple model Hamiltonian where vk prime is just a constant minus v0, whenever k is within a particular range, then the k dependence on this side goes away. And this means that this is a constant. In other words, delta k takes this form. 0 when mod xi k and some constant independent of the k when mod xi k is less than h plus omega c. Okay. So the problem simplifies considerably, although it started out being a problem where you have to find as many deltas as there are k's, and they were complicated. They had a complicated relationship among themselves. Now it's much, much simpler. Delta k is just a single number delta, which means all the delta k primes on this side also has to be a single number delta if k prime is close enough to the Fermi momentum. If k prime is far away, then this side is simply 0. So now, if you do that, if you take this equation and plug this result in that, what do you get? You get, okay, I will have to move away a bit, but you get this very important equation. Delta, which is now what our delta k is, v0 by 2 sum over k prime so delta, I'm just writing in short, but this is really square root of delta square plus xi k prime square. Okay? And this summation is actually restricted summation. That is, this summation is done only where, sorry, because when mod xi k prime exceeds h cross omega c, the delta k prime would vanish. Delta k prime is the constant delta only within that region. Right? And this immediately tells me, gives me a very simple thing, because delta can cancel among each other, right? You get 1. In fact, here in this equation, because there is no k any longer on both sides, there is no trace of the k, I can just get rid of the prime and just say, okay, sum over all momenta of 1 over ek, but it's really not a sum over all momenta, because sum over all momenta such that the corresponding energies is within h cross omega c of mu. Right? So this is a rather nice equation, a simple equation, which is basically the result of the BCS calculation, the final primary result actually. And what this helps us to find out is the value of delta. Can you see how? The delta has cancelled from both sides, right? So how does this help us find out delta? Yes?
So we find k, then we put the value on the formula ek square equals to delta k square plus I k square, then we find delta k.
Well, there is no delta k, right? You just need delta. Just need this number delta, because delta k is delta for our problem. Or other delta k is delta within this range and 0 outside. Remember, this formula is in the context of our present model Hamiltonian. So I just need the value of delta. How do I find the value of delta from this equation?
So if we integrate the remove the summation by integration in the equation of delta.
So where is is there a delta anywhere in this equation left? Has it
No,
cancelled?
sir.
No, but you were right. Actually, it hasn't gone. All of the delta hasn't gone away. Remember, our known quantities were vkk prime, which we have already used, and xi k is unknown, right? Ek sitting here is actually square root of xi k square plus delta square. I'm not no longer calling it delta k prime square or delta k square simply because delta k is the same as delta, right? Is that okay?
Yes, sir. Yes, sir.
So basically, this equation, and you were right, instead of writing this as a sum, what we always do is change it to an integral, which is v0 by 2 integral over xi. You need the number of k values between xi and xi plus dxi as always, and then the denominator here is simply ek. Ek is simply delta square as xi square, right? And the limits are the values which xi take over the extreme region where this integration is done. This summation, remember, is done where xi's magnitude is less than h cross omega c. So xi actually goes from minus h cross omega c to plus h cross omega c. In other words, you are actually doing this over a narrow region surrounding h cross omega c of thickness twice h. So this gap is twice h cross omega c. This thickness from mu, this much below, this much out. Okay. So this is what we need to do. Now, the next step is, of course, to evaluate this integral. And to evaluate this integral, you need to know n of xi precisely. Now, n of xi, one possibility is that you could just use the free particle value for the density of states, which would not be very good because, after all, interactions do change the dispersion relation, right? You should not really use xi equal to h cross square k square by twice and minus mu, because that would be for the free particle. Interactions have changed this relationship for the energy. But we don't really need to worry about that too much. Remember, this is a very thin region close to the Fermi level. H cross omega c is typically much, much less than mu. So what we do, and in fact, this is something we have done earlier also, is we approximate this n of xi by n at 0. That is n exact. 0 here, of course, means xi equals 0. That means the energy is exactly equal to Fermi energy. So the density of states at the Fermi level is what you approximate n xi by. You just say that when xi changes all the way from minus h cross omega c to plus h cross omega c, n xi doesn't get to change that much. It's a slowly varying function. I can pull it out as n0. And then right? Now, this integral is actually rather trivial to do. Well, the standard way to calculate this integral is putting xi equal to delta sine hyperbolic t. Because if you do that, then you get delta into 1 plus sine hyperbolic square in the denominator, which is cosine hyperbolic, and you get the same thing in the numerator. They cancel. Anyway, the result is simply sine hyperbolic inverse. So this gives us an equation for delta. Delta works out to be okay. And in most cases, N0, V0, the potential, which first of all, the potential which binds the electrons together attractively is a very weak potential. So V0 is rather small. 1 by N0, V0 is quite large. And therefore, if X is large, then what is the approximation of sine hyperbolic x? Can you tell me that? When x is large, what is this? So what's the definition of sine hyperbolic x? I hope all of you remember
E
that.
to the power x minus e to the power minus x by 2.
Right. So when x is large, what is the approximation that would be obvious here?
E to the power x by 2.
Yeah, this is actually just e to the x by 2, at least approximate. Okay. Simply because you can ignore e to the minus x in relation to e to the x. And with that approximation, this becomes twice h plus omega c. I hope this formula looks familiar to all of you. And you have seen something very much like this in the Cooper problem. Now, this actually, strictly speaking, works only when 1 by n0 v0 is very large, that is, n0 v0 is very small. In reality, for most of these experimental things, this comes out to be around around 0.3 or so. So 0.3 is not very much less than 1, even then e to the power 1, 0. E to the 1 by 0.3 and e to the 0.3. These two numbers, the e to the t and e to the minus, e to the x and e to the minus x, they actually differ very much from each other. And this is a decently good approximation. So this is our formula for the gap energy. We are going to interpret this as a gap later on, but this is an important result. Okay, and how do you find out the Vk square and Uk square? Well, we are already done, because remember Vk square minus Uk square was simply and Vk square plus Uk square. Sorry, I put the squares in the wrong place. The squares are, of course, for the Vks. 1, which means we are going to get Vk square plus. So all you do is just add these two and half the result. So half into 1 minus xi k by ek. Of course, if you know one of them, the other one is simply 1 minus that. So it's really not important to discuss both of them. But Vk square, this is what it looks like. Once again, let me remind you that in our problem, delta is a constant. At least delta is a constant within a particular region. And then you were to try to look at the graph of this quantity. What would it look like? Note that when xi k is very large negative or very large positive, okay, when xi k is 0, what happens? Xi k is 0, this is just half. And when xi k is very large positive, what happens to this quantity? Sorry, have anybody been saying some things in the middle? Because I lost my earpiece. I've just realized that now.
No, sir.
Okay, so now I'm asking the question. What happens when xi k is very, very large? What happens to this quantity? Very large compared to delta, that is.
Zero, sir. The function becomes zero.
The whole function becomes 0. And what happens when xi k is very, very tiny? It just goes to 1. Goes to Okay, what happens when xi k is very, very tiny? That's an important question. When xi k is tiny, meaning, or sorry, xi k is tiny is really not the right thing to ask. When xi k becomes large negative, what happens to this planet? By the way, even when you say xi k, okay, let me just ask that other question again. When xi k becomes large positive, you said it becomes zero. Why does it become zero? Because delta can be ignored with respect to xi k, right?
Yes, sir. Delta can be ignored and Zyke cancels out. That's
Yeah,
why VK
but
square equals.
actually, it's even better than that, because when xi k is large positive, that means you are very far away from the Fermi surface, right? That means delta is actually exactly zero there. Remember, our delta k
Yeah,
is
yes,
actually
sir.
delta only up to a particular limit. After that, delta k is actually zero. Anyway, the conclusion doesn't change. You don't even have to go. The point is, you even when you go that far away, then this thing actually vanishes. But even if it did not, you could ignore this. What happens when xi k becomes large negative? Even then, xi k square is much bigger than delta square, right? And even then, ultimately, delta actually vanishes, right? When xi k becomes large negative. So what happens to
Yes, sir.
k square there? What
So it
happens to this
becomes
point?
1.
Why? How can it become
So
1?
1 minus of minus 1.
Why minus 1? It's xi k by square root of xi k square, right? We ignore the delta square,
So
then the
xi
square
k
root
is
of,
negative.
then you're right. Then what happens? Xi k is negative, but isn't xi k by square root of xi k square? How much is this? Or x by square root of x square. What is this?
This is
Equal to what?
1.
It's 1. Always. Right?
Yes, sir.
And then that is what we are looking at here. Right? So x, we are looking at xi k. So shouldn't that be 0 again?
So, but since xi k is negative, so the numerator xi k must have a negative sign with it.
What about the denominator?
So it is
In other
squared
words,
and
this result that you're talking about, this is correct for all x's. Is this correct for positive x and negative x both?
so for negative x, this will become minus 1.
Okay. Why is that?
So it will become minus x by x. So
Actually, it will become x by minus x. This is the other way around, actually. X is x, no matter whether it's positive or negative. The important thing is square root of x squared is not x. Square root of x squared. Square root by definition is the positive square root, right?
yes, sir.
That's the definition of the square root function in calculus. There is no such thing as plus minus square root as a function. And that is precisely why you have to say both plus and minus root x when you want to refer to both roots. Square root is always the positive square root. And therefore, square root of x squared is actually the magnitude of x, not x. So when x is positive, this is 1. When x is negative, this is minus 1. So that your statement was right. It's just that you have to be careful about the square root in the denominator. And if you take that into account, this is what vk square essentially behaves like. Okay, my bad. I'm drawing pretty badly, but it goes close to 1 when xi is large negative, goes to half, and then goes to 0 for large values. This actually, Tinkham, for example, reminds you that this looks very much like the Fermi distribution at a finite temperature. Okay,
Yes, sir.
although it's not really the same function, it looks very much like that. Now, so what we have done is we have figured out what the wave function really is like. In particular, we know all the vk's, we know all the uk's. So we know what the wave function is like, at least for this particular model problem. Now, let us try to take a look at, according to this particular model, how much energy is released when you go from a normal state to a superconducting state. That is, how far below is this superconducting state in energy compared to the corresponding normal state. Just to remind you, this is what we were looking at, H prime's expectation value, and that was this. UK prime, sum over both K and K prime. And what we want to figure out is, if you did, for example, if you did not have this superconducting situation, then what would happen? If you had a normal thing, then this energy would simply have been a sum over all the pairs below the Fermi level and 0 for anything above the Fermi level, right? So it would just be this. If the interaction, for example, had not been there, if VK prime were not there, then what we would get is just this term. The question is, how much does the interaction actually change this quantity? How much below are you? And the good thing about, what is the important thing about that? It tells you how stable the superconducting state is compared to the normal state. And in particular, you know this from earlier classes, that magnetization tends to destroy superconductivity. So here, what we are saying here is superconductivity going into the superconducting state lowers the energy from the normal state by a certain amount. If the magnetic field has more than that amount of energy, then it's going to destroy superconductivity. It's going to put you back in the normal state. So this actually allows us to calculate the expectation value, calculate the critical magnetic moment, magnetic field for this particular system. But in order to do that, let's take a look at what this calculation goes as. Well, the first term is simply sum over K twice the IK. I just wrote down VK squared a while ago. VK squared is half of this. So xi k into 1 minus xi k by k. Now this term, okay, let's take a look at this second term in some more detail. Let me just do it this way. UK VK, these are dependent only on K, and sum over K prime. Now, it may be easier to recognize in this form. What is this sum? Anybody? This quantity, Vk prime sine 2 theta K prime, which I'm summing over K prime first. What is this quantity? Have you seen this sum before?
So twice delta K minus twice delta.
Yeah, this was our definition for delta K, right? So in general, for the general model, this quantity will be minus twice delta K. So this is minus half right? But in our model, delta K is a constant, and we already know what sine 2 theta K is in terms of that, right? That's UKVK. Where did I write that? Did I write that before? Okay, delta. Sorry, I missed the place where I wrote that. Anyway, doesn't matter. I can just do it again. Delta k is delta, and this sign. So this is minus delta by 2 that can come out, and you have the sum over k of sine 2 theta k, which is actually delta by ek. Remember this? The sine 2 theta k is delta k by ek, something we found out
Yes,
at the
sir.
very beginning. Okay.
Yes, sir.
But note that you can take the minus delta, this delta out again. Now I'm specialized. This one in fact, this at this step I have specialized to our model. So far, this result was true no matter what VKK prime was like. But when our model has been invoked, where VKK prime is non-zero only over a narrow region, and delta k therefore is a constant only over that region at delta, and this sum over k now is of course with mod psi k less than h plus omega c, right? Because beyond that the delta k will vanish, so there will be nothing in this sum. So get minus delta square by 2 sum over k 1 over ek. But anybody remember what this quantity is? Sum over k 1 over ek over this mod psi k less than h plus omega c region. What is this?
So twice 2 by V naught.
This is actually 2 by v, right? This was our gap equation basically. So sum of this is actually 2 by v naught. So this actually works to minus delta square by v. Okay. So this rather complicated looking interaction term, ultimately when you put in the optimization solution, put in the values of vk and uk you get by optimizing the problem, turns out to be rather simple. You get the expectation of h prime is actually sum over all k of psi k that's a single particle contribution, the psi k into 1 minus psi k by ek minus delta square by v. So this is our expectation value for h prime. Okay. This is of course for the superconducting state. For the normal state, where delta is 0, well, for the normal state, what happens? Let's go back from this. Let's see whether we can recover this from this formula itself. For the normal state, of course, there is no gap. Delta is 0, and that means ek is the same as square root of psi k square. So this simply becomes k equals psi k minus right? Is that okay?
Yes, sir.
And this simply means that this is twice psi k sum and when mod k is less than kf, that means your energy is lower than the Fermi energy, and psi, which is energy minus mu, is negative, right? So there, these two terms actually add. You get psi k plus psi k. Whereas where energy is positive, where psi is positive, that is you are above the Fermi level, then this ratio is simply psi k and the cancel. This is sort of understandable because you are saying that in the normal state, and this is the ground state for the normal condition, without formation of these pairs, you would essentially have the filled Fermi sea. And therefore, you will just have all the energy levels below the Fermi level filled up, and the energy is going to simply be addition, sum of all these energy cycles. The factor of 2, you can simply extend by saying every energy level is occupied by 2 electrons. This is the standard energy that you get at the ground state for free electron theory or any fermionic system, that is. So the excess energy, the energy difference, how much is the stabilization? So this is for the superconducting state, this is for the normal state. So ES minus EN is what you get when you subtract these two quantities. There, better to actually, since this sum is only over mod k less than kf and this is over all k, it's best to break this up into two pieces. For mod k greater than kf, this quantity is just stays whatever it is, right? Because there is no contribution from here. But for mod k less than kf, what happens? You take away, there you take away twice xi k from this. So you get minus xi k. And then, of course, you have minus delta square by V0. Right? So the stabilization in energy because of the formation of this Cooper pairs structure of this superconducting state is given by this quantity, which you can simplify because if you compare this sum and this sum, this is a sum for all energy, all momenta above kf of this quantity, and this is for all momenta below kf for this quantity. But our systems are typically symmetrical about the Fermi energy, right? If they're symmetrical about the Fermi energy, then these two sums actually end up being the same, at least to within whatever approximation we're using.
So
Yeah.
for h prime n, average value of h prime n, there shall be a minus xi k in front. Well, the minus sign has been missed, I guess.
Right. You mean here?
No,
Right.
the minus.
No, I'm just taking this expression. I'm just putting in V0 delta equal to 0 here. Okay. So it's just this expression, no change. You take this expression as it stands, just put in delta equal to 0. Of course, when delta is 0, then Ek is actually mod xi k. I just put that in. And delta is 0 means this term is not there. Right?
So for yes minus c, and why did we write for in the second term that minus xi k squared by ek?
This one. I'm actually
Yes.
I'm writing this term. Okay. This term can be there sum over all k, right?
Yes, sir.
Now, if this is a sum over all k, this is for k mod k more than kf as well as mod k less than kf, right? Now for mod k more than kf, of course you get this. For mod k less than kf, you get this, and from that you subtract twice xi k. Because remember you're subtracting en. This is es, this is en. You're subtracting this. But this sum only is for mod k less than kf. So you're subtracting twice xi k when mod k is less than kf. That's all we are saying. Okay? Is that okay?
Sir.
And now notice that these sums, when you look at both sides of the Fermi level, the minus xi simply says that there is change sign when you're on the other side. But remember, on the other side, on the negative side, or the sorry, not the negative side, but where mod k is less than kf, xi k is actually negative. So minus xi k is a positive contribution. And because of the symmetry about the Fermi sea, these two sums are actually the same. Of course, xi k square by ek actually contribute the same thing, whether it's positive or negative, doesn't matter. You're squaring anyway. But you can just write this as sum above the Fermi level of this quantity. So this is the energy stabilization, which we need to calculate now. Now, of course, the calculation is Es minus En that we are trying to calculate. We can again change this sum to an integral. And also let me remind you that this sum does not really go on forever, because this result is actually true only up to a particular size of mod xi k. Beyond that, there are no contributions anyway. Beyond that, all these terms vanish. So what you get, this is an integral from 0 to h cross omega c, because we are only looking at mod k bigger than kf. So this is an integral over xi.
So
Yes.
so the expression where for the normal energy state, So will it be like in the denominator you have written mod of xi k? So will it be xi k or ek? So for the
No,
normal
it is actually exactly Ek. But what is Ek when you have a normal state? Ek is this, right?
yes sir.
But when delta is 0, then this simply becomes Ik square root, right?
Okay, okay.
And that's mod Ik.
Yes sir. Yes.
So in the special case when delta vanishes, that's a normal situation. Then this Ek in the denominator becomes mod Ik. It's not as if I'm writing something else. I'm just saying Ek's value then is mod Ik. Okay? And now this simply becomes, this integral becomes xi minus xi square. So this is again an integral which would have been complicated if n xi were a complicated function, but within the approximation that we have been using so far, we have been treating n xi as a constant. Oh, sorry, I missed out the minus delta square by v0. So there's a minus delta square by v0 outside anyway. Now, once again, this integral is a rather trivial integral to do. So homework, carry out this integral. This is a pretty straightforward integral, and in particular, it's very easy to do if you make the substitutions I equal to delta sine hyperbolic t and work through this. Now, what I'm going to claim here is that this is what comes out of the calculation. If you integrate this and then, so this is the homework. Homework is reduce this integral expression into this form. The integral can be carried out very easily, but going to this form ultimately requires you to make sure that you're using the approximations correctly. Remember when we wrote this down, the expression for delta that we wrote down here, we had made an approximation that n0 v0 is much less than 1, and therefore the sine hyperbolic can be replaced by e to the x by 2. That is the approximation you have to bear in mind. That's the kind of approximation we are actually using here to arrive at this. So this is the homework. Try to calculate this integral, which is pretty straightforward. And then, which is slightly less straightforward, use the approximations that we have stated, use them consistently to reduce this to this expression. But this actually ultimately gives you a rather interesting result. It tells you that ultimately the energy difference between the superconducting and the normal state at the ground state, that is at of course this is the state the system will be in temperature, in absolute zero of temperature, is actually given by minus half n0 delta square. Is given only by the value of the delta, and everything else goes away from the calculation. And the density of levels at the density of states at the Fermi level. Okay. So now this is the energy which a superconductor loses or they get stabilized by when it goes into a superconducting state. But if you bring in a magnetic field which can give back more than this amount of energy, then superconductivity will get destroyed. And this immediately tells us that for, if I'm using CGS units, this is if the critical magnetic field is given by this, then we can easily see that hc square by 8 pi, that has to be half n0 delta square. In other words, hc. So the critical field which is required to destroy superconductivity is proportional to this gap energy delta. Now that's actually a very nice result for us because of the simple result that this delta is an important theoretical quantity, and the critical field is a very easy to measure and important experimental quantity. So this gives us a way of relating the theoretical predictions of basis theory rather nicely with experiments. We can just check whether the critical, how the critical field depends on delta. Okay. More importantly, okay, now comes an important issue. How do we even know what delta is going to be like? And for that, of course, we have a formula for this. Delta is basically h cross omega c into the power minus 1 by n0 v, right? So delta essentially goes like h cross omega c. The critical frequency is important here. Now, this critical frequency, the physical mechanism behind this suggests that the critical frequency should be related to the phonon frequency, right? To the Debye frequency of the model, the frequency at which phonons vibrate, because it's a phonon-electron interaction which ultimately gives rise to this attractive potential. Now, how could you test a hypothesis like this, that this gap energy, which you can now experimentally determine using HC, how can you actually relate that to the phonon frequency, or how would you actually verify a statement like this, that if a phonon frequency of a system changes, then all other things remaining constant, the gap energy will be proportional to the phonon frequency. Now, for that, there is one very nice experimental observation which has been available for a long time before the theory came about. It was a very important puzzle, so to speak, and we have already mentioned that before. We have talked about the fact that the isotope effect plays a very important role in superconductivity. Isotopes of the same material have different values for the critical magnetic field and the critical temperature, right? Now, if superconductivity had been a purely electronic phenomenon, replacing the nucleus by another heavier nucleus would not have any effect. We would not expect changing one isotope for another to really produce a big difference, because electrons, of course, are the same for two isotopes and they are in the same configuration and so on. Having a heavier isotope simply means that the nuclei take more time to move around, but that should not really affect the electronic behavior. However, what is important in superconductivity is that it's not really a purely electronic phenomenon. Although we are trying to explain it by electron-electron attraction, but the electron-electron attraction actually comes from the way in which the phonons respond, or the way in which the lattice responds to an electron's passage, right? And therefore,
Yes.
this is the important point, that experimentally, now, one thing we know, this omega c, if this is for the phonons, how should omega c depend on the mass of the nucleus? Omega c should be proportional to what? M to the power what?
Half.
Half. Are you sure?
One.
No. Think of a higher secondary. Half was closer. Omega is root over k by m for a spring, right? It's actually minus half. If you remember, when you are replacing one isotope by another, all you're doing is you're putting a different mass in the same potential. So the restoring force is the same. It's just that mass is bigger, so you get a more sluggish. In fact, this is easier to understand qualitatively. If m goes up, the thing becomes more sluggish, right? So the frequency will be less. It will vibrate less number of times. Now, since omega c goes as omega minus half, delta is related to that. This crude model tells us that Hc, the critical magnetic field, should be proportional to m to the minus half, or should be, let's write this in a more sophisticated way, should be m to the alpha, where alpha is minus half. Now, this behavior is actually rather well satisfied by a lot of different superconducting materials. That the critical field turns out to be proportional to the square root of the mass, or inversely proportional to the square root of the atomic mass of the isotope involved. Now, this was one of the big successes of BCS theory, because it was able to predict properly what this is going to be, what various physical phenomena, including the fact that including this particular fact, the isotope effect. Now, of course, you must realize that when I said delta goes as omega c and therefore goes as m to the minus half, I'm actually assuming that V0 and M0, these don't change from one isotope to another, right? Of course, if delta is going to be only proportional to omega c, the rest have to be constants. Now, that is really not a perfect approximation to make. N0 is the density of states near the Fermi level that hardly changes, but V0 often changes. And so, especially for high temperature superconductivity, the behavior is very different often. It is not the form m to the alpha, but alpha is not minus half there. But that is also an important thing, because you can actually experimentally see which superconductors fit the BCS calculation well and which ones don't. And for the ones that don't, you have to think of other mechanisms which are very. So this standard mechanism of electron-phonon interaction producing an attractive potential and hence producing Cooper pairs may not really be very, very correct. They are not very correct for, say, the later day higher temperature superconductors. And one of the ways you can establish that experimentally is just by checking this particular prediction. Okay. So I'm done for today, but next day we are going to do Bogoliubov transformation approach for solving this problem. And that will give us, first of all, the spectrum in a rather nice way. Similar solution to the one that we have already obtained, but it will also give you a way of figuring out what the excitation energies are and how this energy gap in the spectrum really manifests itself. But I think you have already done the Bogoliubov method, at least for magnons, right?
Yes, sir.
So the calculation will be very similar. Basically, you have a complicated Hamiltonian to begin with. Okay, I guess I did not even write down that complicated Hamiltonian today, because I started with the solution. The Hamiltonian, of course, was but this particular problem becomes very difficult to solve if you wanted to try to find out the eigenvalue. Remember, what we have done in the BCS is that we have adopted the variational approach. That is, we have assumed an ansatz for the wave function, a physically reasonable ansatz based on the fact that Cooper wave formation should lower the energy. And within that ansatz wave function, we have found out the parameters which optimize the value for the expectation value of this quantity. However, what we are really supposed to do is solve this for the eigenvalues and eigenvectors of this directly by solving the Schrodinger equation. That is, just use H prime psi equal to E psi. That will give the energies, right? Take this Hamiltonian, apply it on the wave function, and solve for this. The problem, of course, is that this particular term with 4 operators, creation annihilation operators, becomes very, very difficult to handle. It's impossible to handle this exactly. So what Bogoliubov did was essentially approximate this by a quadratic term, simply by saying, okay, we will replace this by an average. And by working with this, he ended up with quadratic, that is, pairwise creation annihilation operators in your Hamiltonian. So once you have that, you can essentially go to normal modes the way you have done in magnons. In fact, the rest of the cells will be almost the same as the one you do in magnons. Whereas where you go from these creation annihilation operators to other bosonic creation annihilation operators by transforming them in a way. So we will take care of that the next day. But okay, one more thing. Next day is Tuesday. Tuesday I have an invigilation duty, so I cannot take the class on Tuesday. In fact, I'm busy on Monday and Wednesday as well. So is it possible for you to have a class on Thursday or Friday? If not, we can meet again on next Saturday.
Friday, we might have to go for a practical. So Thursday, sir, it will be okay.
Okay.
Definitely
Or
Thursday.
maybe we'll do it next Saturday. Let's do it only on Saturday because that's okay. But then we will take a longer class on Saturday. Is that okay with you?
Yes, sir.
Okay, so next Tuesday
Yes,
there
sir.
will be no class. Okay. Okay.
Thank you, sir.
Done. So today we are done.
Thank you, sir.